In the last lecture I introduced APW functions, and I said that APW functions behave like atomic wave functions inside a sphere which encloses the atomic nucleus, and between spheres it is a constant, and I showed how to construct this potential and potential for this system. Now the idea is that the function that you have, which is the plane wave in the between the spheres, and the atomic function inside the sphere must be matched on at the surface of the sphere so that it is continuous. To do this matching, what we have to recognize is that if you look at the plane wave e to the power I k dot r, this is the solution for the free particle. That is minus h cross squared by 2m del squared e to the I k dot r equal to h cross squared k squared by 2m e to the I k dot r. So given this, what we know is that this solution that we have obtained here is in the Cartesian coordinates. This is obtained in Cartesian coordinates. The idea is to obtain the solution. Del squared can also be written in terms of r theta phi coordinates. And if you solve for e to the I k dot r, then the if you solve for the eigenstate of the free particle Hamiltonian, then you can show that e to the power I k dot r can be expanded as 4 pi times sigma over L equal to 0 to infinity, sigma over m equal to minus L to plus L, I to the power L j L k r y L m star angular coordinates of k and y L m angular coordinates of r, and j L k r is the this spherical Bessel function. So what we are now looking for is that supposing I have the following, that is, I have my unit cell here. I am just showing it in 2 dimensions for the sake of simplicity, and I have an atom here whose origin is at r nu, and I have my coordinate system origin is here, and if I am looking at the radius, the radius is s nu of the sphere around the atom at r nu. So this is r nu. Let me take any position r. If this is the vector r and this is the vector rho. So what happens is r I can actually write as r nu plus rho, so that e to the I k dot r can be written as e to the I k dot r nu, which is actually not a variable, which is fixed, and then e to the I k dot rho. Now we can expand e to the I k dot rho in exactly the same way as before. So now what happens is that if I want to match the wave function inside the sphere with the plane wave on the outside, then I have to look at the following: k of r, k comma r at the, I think I had written down last time, chi rho is what I have to write. Chi rho is given by this expression Okay. So, we have to find out what is ALM. Chi k comma rho is equal to sigma over L sigma over m ALM, which is a function of kr or r, let us say, which is a function of rho times YLM star k YLM rho. And if I want to calculate what is ALM rho, then it is quite simple. All I need to do is write down the expression for e to the ik dot r is equal to e to the power ik dot r nu e to the ik rho and ik dot rho, because rho is still a vector here, and I can write it as simply equal to e to the ik dot r nu sigma over L equal to 0 to infinity. Let me also take 4 pi outside, and I have sigma over m equal to minus L to plus L I to the power L j L k rho y L m star k y L m rho. Rho is the angular coordinate. Now, all I need to do is multiply by, to get ALM of rho, all I need to do is multiply this by y star LM and then integrate. Okay. So, or rather let me say that I equate the two things. So, which means that at the surface what we have is JLK rho is equal to JLK S nu, and so this should be at the surface this thing becomes 4 pi e to the ik dot r nu sigma over L is equal to 0 to infinity, sigma over m is equal to minus L to plus L I to the power L j L k S nu y L m star k y L m rho. Inside the sphere, the wave function is actually given by, we had the expression earlier. So, let me go back to the expression. We had the expression chi rho is equal to L equal to 0, m equal to minus infinity to infinity, A L m y L m rho, R L epsilon rho. I think I made a mistake in actually getting the stuff there. So, this should be actually y L m rho R L rho. Okay. Because is a linear combination of the angular part of the wave function, which is y L m, and the radial part of the function, which is R L rho. So, now if I equate the two things, what I will get is the following. Inside the sphere, chi at the surface of the sphere is, well, let me say at the surface of the sphere is going to be R nu, or let me write down first rho and that replace it by surface of the sphere. So, this is equal to sigma over L is equal to 0 to infinity, sigma over m is equal to minus L to plus L. I have A L m y L m rho R L rho. So, on the surface of the sphere this quantity gets replaced by S nu. So, inside the sphere this is the thing on the surface of the sphere. We have chi rho on the surface is equal to sigma over L is equal to 0 to infinity, sigma over m equal to minus L to plus L, A L m y L m rho R L S nu. S nu is the radius of the surface. Okay. So, if we equate this to this, we get the expression for ALM, which is given by the following: 4 pi e to the I k dot r nu I to the power L y L m k j L k s nu divided by R L s nu. Okay. So, this will be the coefficient, the thing, and the unique thing about these augmented plane waves is that APW functions, basis functions, are taken to be continuous across the surface of the sphere, but not differentiable. It does not matter if the basis function is that, because what we are interested in is this thing, the acceptable eigenstates will have both continuous this thing in value and in slope across the surface. So, although the basis is not continuous in slope, but it is continuous in the eigenstate will be continuous. So, one need not worry about that we can have discontinuous basis. Now, having said that, now let us see how to compute the matrix elements between APW functions. To be able to compute APW functions matrix elements, we must know how to compute kinetic energy across the discontinuity in slope. So, this is a little tricky, but I will just show you how by taking recourse to this in Gauss's divergence theorem. We know, for example, from Gauss's divergence theorem that the flux through a surface, which is given by E dot dA, dA is the area element and E is the electric field, and the area element is directed perpendicular to the surface. This is equal to grad rather divergence E dV on the volume. Okay. So, we can also write it as, because E is grad phi minus grad phi, it is also written in the following fashion: integral over the surface grad phi dot dA is equal to minus del square phi dV. Okay. So, given this, you see the nature of the operator. Okay, so the nature of the operator is minus del squared, and this is our volume. So what we can actually do is across the surface the discontinuity in derivative leads to a flux which can be written as say, I mean, I am also multiplying by u star in the case and then multiplying it. So, but nonetheless I can write it in the following fashion: integral grad u outer minus grad u inner time dot ds is equal to integral over volume del squared u dv. So this is a form that you can see. See, use uo is the derivative which is taken with respect to outward perpendicular to the surface. So it gives a flux that is going out of the this enclosed region, and ui is the inward. Okay. So because of this, one can write down the kinetic energy that comes from this part. The kinetic energy for a general discontinuous surface can be written as one half of integral over the surface, which is in our case a sphere, the wave function phi 2 minus phi 1. I will just write down what are phi 2 and phi 1 in a minute. Del by del rho phi 2 star, rather phi 2. So there is no star here. The other one has a star. Phi 2 star plus del by del rho phi 1 star plus phi 2 plus phi 1 so this whole thing is plus phi 2 plus phi 1 del by del rho phi 2 star minus the star will now go on the other one, del by del rho phi 1 times ds. So this is the contribution that is coming from the surface term. In general, when phi 2 is the function in one region, inside the sphere or surface, whatever you want to call. In our case it will be a sphere, and phi 1 is the function outside the surface. So what we can actually now do is write down the matrix element Hij for two plane waves, not two plane waves, two APWs with wave vectors Ki and Kj as Hij is equal to integral over 1 plus 2 chi I star H chi j d tau plus an Sij term, and Sij is equal to minus 1/2 integral over the surface chi 2 I plus chi 1 I star del by del rho chi 2 j minus del by del rho chi 1 j ds. So, chi 2 and chi 1 correspond to the two regions 2 and 1. The two regions 2 and 1 I will just show you. So, this is region 1 and this is region 2. So, region 1 is the constant potential region and region 2 is inside the sphere. And then I also have a integral which is the overlap integral, which is integral over 1 plus 2 chi I star chi j d tau. Let me just make sure that I have not interchanged region 1 and 2 by accident. Yeah, region 1 is inside the spheres and region 2 is outside the spheres. That is the notation that I am going to be using. This is region 2 and this is region 1. Okay, so that is how I have used the notation. Okay, now having done this, let us see how we can evaluate these things. So, of course, once you have all these things, then we just have to solve the matrix equation. So, the solution is obtained by solving the system of equations sigma over j Hij plus Sij minus E delta Ij Cj equal to 0. This is the usual thing that you get by by minimizing the expectation value of the integral involving the Hamiltonian with respect to the coefficients Ci of the APWs in the expansion. After having done that, let us see the solution is going to be the following. That is, in region 1, we solve the radial equation solved for a specific energy E prime. So that the Hij minus for region 1 H1 Ij minus E delta Ij in the region 1 is equal to E prime minus E delta Ij. it looks like when you do this, E prime is the energy for which we solve this. E prime is the arbitrary energy. So, you set up the Hamiltonian matrix. What happens is that the Hamiltonian matrix becomes Hamiltonian matrix elements depend on E prime through the radial functions RL E prime comma R. Now, because of this dependence, your Hamiltonian matrix element depends upon energy, and your eigenvalue also depends upon the Hamiltonian matrix, solving the Hamiltonian matrix for its eigenvalues. So, usually E prime is not equal to E, which is eigenvalue of the Hamiltonian matrix, eigenvalue of the full Hamiltonian matrix. So, you solve for E prime, obtain a E and plow it back into the radial Schrodinger equation within the atomic region, and solve once again for that particular energy and do it self consistently until self consistently we solve this. We solve for E prime equal to eigenvalue of the Hamiltonian matrix. Of the crystal. E prime is the eigenvalue of the radial equation, but that should be equal to the energy eigenvalue of the crystal Hamiltonian. So, which means that it is actually a nonlinear equations is what you have to solve, nonlinear equations. But the convergence is pretty rapid. And this was the method that was used initially for doing these APW calculations. But in the present day, of course, it is done differently, and I will talk about it later. In the next lecture, I will talk about how we can actually get the matrix elements for H2 and H1 and the Sij terms, and then we will continue from there. So, for now I will stop at this point and we will continue again later.